me start recording.
Your time begins now.
Okay, so this is the Sticks and Stones computer problem 2. And I'm Dylan.
I'm Benito, and I'm in my car.
Okay, so there we go. Okay, binary representation. So binary is a numerical base using 0 and 1. It's used for computers. Zeros represent a low and ones represent a high. In digital electronics, we would call the low 0 volts typically, and the high would correspond to 5 volts. So if you wanted to make these logic gates out of like diodes and transistors, that's how you would read the zeros and ones. Mechanically, the way we did it, or I guess the way the problem asked for it, was to have popsicle sticks at like angles where the low or down pointing side of the popsicle stick corresponds with the 0 and the high corresponds with the 1. So logic gates are like structural and architecture components of digital systems like computers. And you can build interesting circuits with them. And what happens is you take binary inputs like 0 and 1, and you get binary outputs depending on what logic gate you put it through. And there's 16 different possible binary outputs given just 2 binary inputs. Some of them are useless, like you put in any number and you're always going to get out 0. That's not a very useful logic gate, but it exists. So we're going to talk more about the useful logic gates. Before that, we'd like to get into truth tables and logic theory. Benito?
Oh, yes, hi. Yeah, so essentially truth tables just kind of give us an expected binary output for the inputs you can put into a logic gate. So on the right, we have like the statements for true and false given, the true and false logic given the inputs and outputs. There's also the concept of Turing completeness. So the Turing completeness essentially means that a system can adhere to a set of rules the same way that a Turing machine can. Turing completeness is kind of the reason that you can build all those cool redstone stuff in Minecraft, is because the system in Minecraft, I believe, is Turing complete. And we will be approaching the theoretical aspect of it through simulating the logic gates in Python.
Okay, so the first gate went over the and the truth table just says that if you put in 2 low outputs, you get a low output. The only way to get a high output is if both inputs are high inputs or ones. And then I define that in Python by saying if the input A and the input B are 1, return 1, else return 0. And then over on the right is the console where I showed that does simulate the logic gate. And it matches the theory of what the logic table says it should do. And then our mechanical representation. Benito? Okay, I'm not sure what's going on with Benito. He's probably muted, but the symbol on the left side is what the AND gate in, I think it's Boolean. That's like if you're going to draw a circuit diagram, that's the symbol that you would use to represent it. And then the way we did it with popsicle sticks is we have the output is labeled on the right, and the 2 inputs are given on the left. And that's kind of where like the black magnetic strips are. So if you press down on that popsicle stick, like I'll show in the video, the output will go up, whereas right now it's down. So I will show that right now. And the inputs are 1 in the picture, but when you push down on it, the inputs become 0, so then the output becomes 0.
Yeah, and in the video it breaks, but it does. Sorry, my internet went down.
Okay, no worries. For the OR gate, we have what happens is the output is a high output when it is either input is 1 So the only way to get a low output is for both inputs to be 0. And then that's just the code, and the console matches the logic table, which is what we wanted. And then
Yep. And then here we have the experimental construction. So essentially the way I went about it is the inputs, instead of being on top of the first seesaw, they are now below it, so that when one of them is 1, it makes it such that the output is 1.
okay, so the NOT gate is interesting in that it only takes 1 input, but then you only get 1 output. And all it does is invert. So if you give it a low input, you get a high input, and vice versa. And the code matches the logic table, which is our goal.
And it's pretty straightforward, as was covered in the question, is that a single seesaw is the NOT gate.
Oops.
It matches the logic.
Ah.
Okay, let's speed run the next couple.
Yeah. Okay. So this is the exclusive OR gate. Basically, if the 2 inputs are different, you get a high output. If the 2 inputs are the same, you get a low output. Code matches the logic table, or the truth table, which is good. Now it's
And
a bit
then-
of a,
Yeah, and then for the experimental aspect, it got a little hectic. I had to use paper clips to extend switches to split them. But essentially, it's composed of a NAND gate, which is an AND gate followed by a NOT gate, and it matches the logic too.
now when we get into the 4-bit adder, it gets very interesting. There's 2 types of adders. This is the half adder. I'm gonna go quickly, but basically you get a way to get binary inputs to sum. And then as you add each bit, you have 2 inputs. So then you get to add more numbers. So you can add up to 8 with the half adder.
And for the 4-bit half adder, I was not able to build it, but we had general ideas. We would have this, the exclusive OR gate at the top, and then have it split between the A and B inputs split, and then have the carry composed of an AND gate. But we ran out of time.
Okay, I did the coding for the full adder, but I'm not going to go over it because I don't have time, probably. That's a thing. It does like a ripple carry thing. I can talk about it later if there's questions. And then our interesting thing was multiplexing, where you have 2 signals and you can select one. And that's the truth table and the code, and the logic, or the output matches the logic. And then
Yep. And then here was our experimental. So the top seesaw is the selector, which will kind of select which output you get. This was inspired by a Minecraft video, because it's the only way I could get to visualize how the gates are supposed to look.
I feel terrible interrupting, but unfortunately your time is up. Were you close to the end of your presentation?
yeah,
Yeah,
I think that was
Oh, perfect. I felt bad about that because it's very interesting. But 4 minutes of questions begins now.